Hi, everyone. We're just going to give it a couple of minutes here, and then we'll get going.
Hey, Connor, we're at 50 plus, so maybe we want to get started.
Sounds good. Hello, everyone, and welcome to Denver Startup Week Virtual 2020. I'm Connor Swanson, the Developer Track Chair and member of the Denver Startup Week Organizing Committee. Thank you for joining us for the first ever Denver Virtual Startup Week. 2020 has taught us anything. It's that we are more powerful when we come together as a community to share ideas and help make each other better. And here we are virtually showing the world what Denver is made of. At Denver Startup Week, we strive to make our sessions a space where attendees can connect, learn, and grow, regardless of gender identity, gender expression, race, ability, sexual orientation, and the combination of those identities. There is something for everyone at Denver Startup Week. Thank you for joining us. With that said, I'm pleased to introduce you to our speakers today, Amal and Scott from the team at Quizlet. I will turn it over to them, and let's kick off with the first Developer Track session of 2020. Thanks, guys.
Thanks, Connor. Good morning, folks. Welcome to this talk, Monolith and Microservices, a false dichotomy. I'm Amol Deshmukh, Senior Software Architect at Quizlet, and I'm based in the San Francisco Bay Area. I started at Quizlet a little over 2 years ago. Prior to that, I've worked in various backend and infrastructure engineering roles at Salesforce, Twitter, and Yahoo.
Hi, I'm Scott. I'm a software engineer here at Quizlet Denver, who's focused on internal search. It's been a blast watching our Denver team grow from 7 people when I joined to around 30 people now. Before Quizlet, I worked at places of all shapes and sizes, a Fortune 500 insurance company, a small local software company, and an early stage startup.
Before we get started, we wanted to take a moment to thank the title sponsors for this event. This talk is about our engineering efforts at Quizlet, and we're proud of the fact that Quizlet is also the Developer Track sponsor at Denver Startup Week. Also, a quick shout out to all the event organizers who've been very resourceful in making this event happen under these very challenging circumstances. And a huge thank you to all of you who are attending this talk live. Thanks for registering your interest, and thanks for being here. Scott and I hope that you find some interesting takeaways from this talk, and we hope that it inspires or informs similar efforts on your end. So we're here today to discuss elements of our software architecture strategy and what's been our experience in dealing with engineering problems resulting from success and growth of our product. Our strategy over the last couple of years has been to continue to evolve the monolith even as we are introducing microservices. In the rest of the talk, we will discuss the rationale behind the strategy, our approach in putting it in practice, and the results we've had thus far. With that, here's the outline for the rest of the presentation. Scott will set up the context with a brief talk on Quizlet's growth that drove the need for an architectural transformation. I will then introduce Quizlet's thesis on adopting microservices, followed by a walkthrough of Quizlet's microservices journey thus far. Next, Scott will discuss the highlights of our efforts to modernize the monolith even as we worked on adopting microservices. And finally, we'd like to summarize the state of our monolith and microservices architectures as they are today before concluding with some thoughts on the road ahead of us.
Thanks, Amol. The goal of sharing Quizlet's growth story is to establish an atmosphere around this architectural transformation talk. I'll spend a few minutes introducing our company mission, provide some history, and we'll bootstrap context of our tech stack. There isn't a one-size-fits-all approach to software architecture. We hope knowing where we came from helps you transfer our learnings to your environment. Quizlet's mission is to help people practice and master whatever they're learning. Essentially, we provide a digital flashcard platform with different study tools, and we remember things people have already learned so we can suggest things to practice. As our user base and product has grown, we continue to focus on the practice to mastery loop of the learning progression, using learning science to drive product development. Quizlet was created 15 years ago in 2005 by a high school student who wanted to build a website to replace paper flashcards. In 2010, Quizlet reached 1 million users. Growth continued at a slow and steady pace. In 2016, with cash in the bank after our first round of funding, we entered a year we could call the year of Beyonce. Beyonce was a user interface overhaul project where we completely redesigned Quizlet's user experience. Also this year, our current CEO joined and we introduced Quizlet Live, our popular classroom multiplayer game. Live's a pretty cool story. Its inception was a result of one of our hackathons. In 2018, Quizlet joined the Denver community with its first 2 employees. Today, Quizlet Denver has around 30 people. And today, in this incredible year of 2020, Quizlet's data is big. We host over 450 million study sets. Continued growth shows our focus on international learners is paying off. All right, on to the tech stack intro, starting with compute, or if you prefer, our web servers. Beyonce is a great place to start. Prior to Beyonce, we were running PHP 5 code on an execution environment called Fast CGI Process Manager, or PHP FPM. We switched to the Hip Hop Virtual Machine, or HHVM execution engine, a technology developed by Facebook. At the time, HHVM was a drop-in replacement for PHP FPM, giving us a performance increase through use of a just-in-time compiler instead of interpreting code on the fly like PHP FPM does. We aren't the only organization to make this switch. It was experimented with and implemented by other large-scale websites too. The HHVM execution engine is really built for a programming language called Hack. Hack could be called a flavor of PHP, but lately it's matured into its own language. Hack provides strict type checking and some other language benefits that weren't available in PHP 5. But the coolest thing about Hack is it allowed for an incremental transition from PHP. We didn't need to stop, drop, and rewrite the code base to realize language benefits. We could migrate code one line at a time, maintaining productivity while enabling underlying language improvements. I think you'll find this concept of don't stop the world to make something better a theme today. We stay productive while making improvements. All right, data time. Our main data store at Quizlet is a relational database, MySQL. MySQL tables are organized across multiple databases with a default catch-all database for most tables. High demand tables are isolated in their own database. Each database has one read-write main instance and then 1 or 2 read-replicate instances. We don't use joins when querying for data, quite a change for me compared to other code bases I've worked on. But now I see how this has helped us reduce the number of scaling gotchas as data size grows. At the early stage startup I worked at, it was super common for complex queries to all of a sudden stop stuff from working as we scaled. I found this problem to be much less common at Quizlet. In the same spirit, we don't use foreign keys. Database relations are defined as ORM level associations, not database level foreign key references. We lose some database enforced safety with this approach, but the mental model agrees more with our query philosophy, and our database is relieved of some chores that it would be required to do if foreign keys did exist. Partitioned tables help with initial data scaling challenges, but with ever-growing data, partitioning is realistically just sweeping a problem under the rug for another day. We vertically scaled MySQL to run on huge Google Cloud VM instances, which have 32 virtual CPUs and 208 gigabytes of memory. Some of our largest databases have tables that hold billions of rows and take thousands of writes per second. And with this setup, our queries are fast, with typical query times less than 5 milliseconds and a P50 query latency averaged over the past month under 900 microseconds. Adding a caching layer in front of a database query is another common way to help scale data retrieval. Our caching layer is provided by Memcache. Due to the simple joinless and default fetch-all nature of our data retrieval, queries are easy to cache and retrieve in Memcache. Finding this data based on user-defined queries is not efficient using MySQL. So we index searchable data to ElasticSearch via an asynchronous task system we call DJP. Like MySQL and Memcache, ElasticSearch was also hosted on virtual machines. When application code execution was the limiting factor for handling user requests, our monolith would scale compute power horizontally using a Puppet-based configuration change. We would manually scale compute VMs based on seasonal traffic. Code deployments to these compute VMs leveraged a blue-green pattern, in which the VM would maintain a repository of recent builds. Then, configuration would modify the load balancer to point to one of two web server processes on each VM. While growth kept happening, we were storing more and more data, and consequently, MySQL would become unstable under heavy load, especially for high write events like saving learn mode answers. This added complexity for necessary tasks like schema changes in large tables, and our blue-green deploy strategy on VMs became fickle as high traffic was routed from one build to the next. Organizationally, unclear boundaries required the introduction of manual flow ownership strategies to triage bugs and delegate improvement ownership to specific teams. Okay, I hope you're able to take away a baseline understanding of Quizlet and our growth. Now, Amol's gonna take over and discuss our architectural strategy for mitigation of growing pains while keeping up with product feature improvements.
Thanks, Scott. Yeah, so we were having scalability challenges, and the growing monolith code base was also a cause of concern from a developer productivity point of view. But I'm sure many of you here will agree that as an engineer, these are the good kind of problems to have. Now, while all fingers were pointing at the monolith architecture, we were well aware that microservices were no panacea either. And as many of you might know, the tide has already begun to turn, even in the community, as many will now acknowledge that a transition to microservices was not necessarily the silver bullet for their problems. A number of cautionary tales are surfacing, and an increasing number of folks have started experiencing the flip side of adopting microservices architecture. Now, some of us at Quizlet have also had experiences with using microservices, as well as making transitions to a microservices architecture before joining the company. So we were well informed, and we decided to take a thoughtful approach to adopting microservices rather than simply approaching this as a case of breaking the monolith. So that brings us to our thesis on introducing microservices in a monolithic architecture. A quick disclaimer here, we haven't submitted this to a conference yet, but today I'd like to share a visual abstract of this with you. Okay, so that's obviously a joke, but just as this meme goes, we asked ourselves, why couldn't we have both the monolith and microservices running side by side and consider that to be a healthy state to operate in? And this occurred to us quite naturally because despite some of the engineering challenges we've had with the monolith, there were several things that were going quite right with it. For a vast majority of use cases, monolith was still a very productive stack to deliver features. So first and foremost, we wanted to acknowledge that fact. And while microservices promised a new decoupled architecture, it would take a while to realize that even if things went perfectly according to plan. Meanwhile, any improvements we made to the monolith had the potential to improve the situation for the majority of the engineers at Quizlet. So we chalked up these guiding principles for the architectural transformation. Firstly, we were all aligned on the fact that when presented with a classic build versus buy question, we were biased towards the buy side, biased towards adopting managed solutions. In fact, even amongst the SaaS solutions that we would consider, we have a preference for the solutions provided by our cloud vendor, Google Cloud. Secondly, we consciously decided to strive for architectural simplicity. So for instance, we decided to constrain our initial efforts to developing microservices that were only accessible in the backend and were just one hop away from our monolith. In this model, access to the microservices is only allowed by the monolith, and we trust the monolith to resolve the user identity before making requests to the microservice. In particular, this means that we can offload concerns like user identity and authorization completely on the monolith. Now, distributed auth is not necessarily very technically challenging because, we could just use JWT to relay identity to the microservices, for example. But then this brings the associated problem of managing secrets, which introduces another vector for troubleshooting and so on. And more broadly, this architectural simplicity also meant that we wouldn't get into a situation, at least early on, where we'd have a graph of dependent services. Then the next point is about managing infrastructure. We renewed our commitment to managing all of the new infrastructure as code. This was not a huge leap forward at Quizlet. We've always managed our infrastructure using Puppet, like Scott mentioned earlier. But in this case, we took a fresh look at the options and quickly settled on using Terraform for both microservices and Monolith. And while we worked on developing microservices, we wanted to bring our monolith on the same infrastructure substrate. This meant that we would invest in containerizing the monolith and the supporting services and deploy them on Kubernetes as well. With that, let me proceed now to talk about our microservices journey. So yes, microservices, they're not the new kid on the block anymore. They're generally regarded as a more sophisticated architecture compared to the monolith architecture. And the expectation here is that that sophistication, primarily as a result of loose coupling across distributed components, enables high scalability and high productivity. And yet I believe they're still not very well understood. There are varying definitions of what actually constitutes a microservice. For instance, some opinions suggest that the core concept with a microservice is the bounded context. And you can find multiple blog posts and articles that support this point of view quite convincingly. But then there are others that just as convincingly argue that bounded context should not be confused with what constitutes a microservice. Now, Martin Fowler is one of my favorite tech personalities, and as far back as 2014, Martin Fowler and James Lewis had described the essential elements of the microservices architectural style. By and large, this description resonated with us. And so to ensure that our initial efforts started off on the right foot, that we were focused in the right direction, we decided to clearly define what microservices architecture meant for us at Quizlet. And the reason we felt empowered to do so is because we had a close understanding of the kind of problems we wanted this new architecture to solve. We were not simply following a model that had worked for some other company in dealing with their growth problems. Because some of the well-documented success stories with microservices transitions were carried out in a different context. They had a different pre-existing state, different state of art with respect to the infrastructure automation and tooling that was available. So we knew that simply translating someone else's solution to our world was not a path that was going to help us. And in general, I'd say that having a deep understanding of the problem you're aiming to solve is extremely, extremely important before embarking on any architectural transformation. Because once you have a deep understanding, you will feel very confident in defining how exactly you want to go about with this transformation. So in our case, these are the higher order bits that we aligned on. Firstly, we wanted these microservices to be deployed separately from the monolith. If you caught this on the previous slide, this is one of the key aspects of a microservice in James Lewis and Martin Fowler's observations. And the reason this is important is because it is the key step towards realizing non-functional benefits like independent horizontal scalability and fast time to recover. It's also something that improves developer productivity. The argument here is that once you've carved out an independently deployable unit of business logic, you have a unit that has a smaller rate of change compared to the monolith. And this smaller unit is also easier to test and deliver continuously. Secondly, we wanted to ensure that microservices completely encapsulate any state that they manage. Any external access to the underlying state must happen via the microservices API. This constraint limited the choice of problems that we could pick early on for extracting a microservice, but it meant that we would be in a lot more control over the implementation of the microservice. And finally, we wanted to ensure that we allow the microservices to be developed without constraints on choice of tech stack. This meant that the teams would have freedom to pick a programming language, choice of storage, all of that. This is clearly different from how we manage things in the monolith world, since the monolith, Scott mentioned this earlier, is developed in Hacklang and uses MySQL for storing data. Also, in our case, the SRE team manages critical changes to the database, like schema patching or running large data fixes. And the SRE team also typically diagnoses issues with VMs, failed deployment, supporting services, etc. Now, autonomy is something I want to talk about a bit more in the next few slides, because I think this is one aspect that is commonly misunderstood, or at least not stressed enough. And the lack of holistic approach towards autonomy could be a contributing factor for a failed microservices strategy. So a holistic look at autonomy must consider service ownership. Service ownership is complementary to autonomy in that sense. And this is best expressed in the form of Peter Parker principle, also known as the Spider-Man principle, if you will. With great power comes great responsibility. Now, we know that microservice developers can and should have the flexibility of selecting the language, stack, and runtime. It's one of the highlights or the plus points of moving to a microservices architecture. But at Quizlet, we emphasize the complementary side as well. And thus, to rephrase this in a holistic way, we say that microservice owners have the flexibility and bear the responsibility of managing their runtimes. At Quizlet, microservice ownership means that aside from developing the service itself, the team is responsible for ensuring that the application provides sufficient visibility into its runtime characteristics, setting up metric dashboards, configuring the necessary monitoring and alerting, and also being on call 24/7. All of that is the responsibility of microservice owners. Of course, this assumes that some basic infrastructure to enable all of this is in place. And we'll talk a bit more on that a little later. Okay, but so I hope that everyone agrees that ownership, at this point, that ownership is an important aspect. There's a range of areas that surface up when we talk about ownership. For instance, how do you manage secrets? You know, if the service uses credentials to access cloud storage, how are they managed? Minimally, you want to ensure that credentials are not committed in plain text in source control. But even going beyond that, should it be possible to rotate these easily? Because that determines how fast you can react should the secret get leaked. So there are a host of such non-functional concerns that microservice owners would be presented with. Now, we recognize that microservice owners needed to be well informed about these concerns, but we also did not want to lay an unnecessarily high bar upfront to get things rolling. So to ensure a pragmatic approach towards this, we devised what we've termed as a services maturity model. The services maturity model defines the minimum bar for non-functional aspects that a service should strive to meet. And it's defined in terms of levels. The levels themselves are really expressed in terms of how critical a service is to the user experience. So at level 1, we say it's intended for production services where the failures would not be noticeable to the end user. An example here would be a service at Quizlet that flags spam in user-generated content. Because this runs purely in the backend and has no user-facing implications, this is a level 1 service. Level 2 is for services that directly affect the user experience. So in a manner so that failures in the microservice will manifest as anomalies to the user. And level 3 is intended for laying out the minimum bar on non-functional aspects for services that are relied upon by other production services. Now, again, if you recollect the architectural simplicity that we're striving for, we don't really have a need for level 3 service yet, but we wanted to be prepared should such a need arise. And having this in place also provides guidance to services at level 2 should they choose to up-level their non-functional behaviors. So putting it in practice involves service owners self-assessing their readiness against a checklist of concerns at the appropriate level. They do that by filling out the checklists, which are just markdown files that then get committed in their microservice repository. Now, early on, I said that we wanted to take a cautious approach to introducing microservices at Quizlet, and let me outline that process. Our first goal when we started about 2 years ago was to gain a good understanding of containerization and Kubernetes. And so as a first step, we decided to pick a trivial problem to containerize. The next goal we decided would be to pick a real engineering challenge, a problem that also has a business impact. We then planned to pause to reflect on how far we'd have come and whether there were any cross-cutting problems across microservices that we should be solving to make our microservices platform more productive. And at that point, we thought we'd be better informed to proceed on taking more ambitious use cases. In the next few slides, I will discuss each of these steps in a bit more detail. So as our very first effort, we decided to containerize 2 data science services. These were Python Flask applications that loaded machine learning models at startup and then served read-only traffic. We migrated these services to run in Google Kubernetes engine clusters. In terms of immediate business value, nothing had changed materially as a result of this effort. But the goal here was simply to familiarize ourselves with this new paradigm of containers and Kubernetes. So very modest beginnings, if you will, but the lessons learned from this effort informed further steps towards tackling a real engineering challenge. One of the things we figured out in this phase was how we could ensure strict isolation between microservices, as well as between the development and production environments. Because with Kubernetes, there are several means of isolating workloads. You have namespaces, node pools, clusters, networks, etc. And in our case, based on our experiences, we decided to use namespaces for isolating different microservices in the same environment, and decided to use Google Cloud projects for managing strict isolation between development and production environments. And these are not very obvious choices, folks, because authoritative documentation from Kubernetes or from Google Cloud does not have a clear recommendation on how to manage these concerns. Now, once we had a good working understanding of Kubernetes, we decided to pick a scalability problem in the monolith. In one specific case involving the largest of our databases, we were experiencing stability issues at peak traffic. If you recall, Scott mentioned this when he talked about our growing pains. And okay, so when I say instability, like we are looking at a few minutes of partial failures per week of peak traffic period. And the partial failures affected how we recorded study activity data. So one might say, what's the big deal? What's the business impact here that necessitates investing in an architectural solution? Well, to answer that, consider this perspective. When we fail at peak loads, we are failing some of our users just when they need Quizlet the most, because the times when we experience peak traffic is also when students are preparing for finals or for some other popular competitive exams. Or consider other times of peak traffic when it's the start of the school year. At this time of the year, a big fraction of the affected users are new users on the platform. These users might not return after this bad first impression. In addition to bad user experience, whenever this happened, it required engineer time to triage the problem, take steps to mitigate the issue. All of this takes valuable engineering bandwidth, which could otherwise be focused on forward-looking work. So this was indeed quite an important problem for us to solve. And because this affected a core part of the functionality, we knew we needed to make this transition without taking any downtime. So with that, here's a 60-second look at the changes that were made over the span of, that were carried out over the span of, I'd say, roughly 5 months. So we started, of course, with the monolith serving out of a MySQL database. We already had a weekly job that copied MySQL data over to BigQuery to make it available for analytics. We started by re-implementing the relevant parts of the business logic in the microservice. The microservice in this case was backed by Cloud Spanner. For those of you who may not be familiar, Cloud Spanner is a horizontally scalable and strongly consistent, highly available relational database from Google Cloud. Okay, so once the microservice achieved feature parity with the monolith, we load tested and profiled it. In this process, we were able to identify and fix performance issues even before we had started taking production traffic. Then we wrote a facade in the monolith which encapsulated all access to the database. This facade was a way for us to manage dual writes to the database. This was followed by backfilling the data from the analytics database to the Cloud Spanner backend for the microservice. So at this point, both the microservice and the monolith have identical data, both from the past and going forward. And then we decided to shift reads over to the microservice. Now, it's not clear from this animation, but this is something we spent a bit of time on because we dialed up the reads incrementally. These were reads across various use cases. And this process took the order of several weeks. We wanted to be cautious and allow ourselves time to analyze the performance and the health of the system. And this is why we proceeded very cautiously in dialing up the reads to the new system. And once the reads were all shifted over to the microservice, we stopped dual writing the data to MySQL. This was effectively the point of no return since the MySQL databases now would not have the new data anymore. And after this, we finally decommissioned the MySQL databases. The final step for us was to change the direction on the ETL. For now, the ETL copies data from Cloud Spanner into BigQuery. So once again, we learned a lot in this process. To highlight just a couple of things, we discovered that Kotlin and Spring Boot offered a highly productive setup for us to develop microservices. Our monolith is developed in Hacklang and it uses custom API and persistent frameworks. With Kotlin and Spring Boot, we achieved the equivalent behavior with not nearly as many lines of new code. And by using one of the runtimes that is supported by Google Cloud, because this was now on the JVM, we were able to profile our code with insignificant performance overhead, even in production. So Cloud Profiler is a sampling profiler from Google Cloud that provides a standard flame chart visualization of the profile. And setting this up involves just a couple of lines of configuration, and this service is free of charge on Google Cloud. But most importantly, we realized that rebuilding a key part of our monolith in a microservice was not the very hard part at all. The hard part really was refactoring existing code and carefully introducing the calls to the microservice. That work, if I was to take a swag, it's just like, I think it was like 3 times as much as building and testing the microservice itself. So at this point, we paused to reflect on how we were working in this new paradigm. There were some solutions that appeared to be hastily cobbled together. In particular, we did not have a great story for deploying containers to Kubernetes. Every deployment required developers to update the Docker image tags in the Kubernetes manifest, and then trigger the deployment using kubectl. So we realized we really needed a first-class CD solution. We also learned that with the level of autonomy we had granted service owners, now it was not sufficient just to understand the application stack in order to develop and operate a microservice. Microservice owners now needed to understand several layers of technologies. First, there's Docker, then there's Kubernetes for managing the runtime. Now infrastructure was being expressed in Terraform. So there's like multiple layers, and all of this imposes a great deal of cognitive burden on microservice owners. And we thought that developing a microservice should not require a mastery in such a wide range of technologies. So we want our microservices platform to be simple for infrastructure novices, but we want it to be accessible to advanced microservice owners at the same time. So we manage this tension by having a team dedicated to managing the microservices platform. After a microservice is onboarded, microservice owners have a choice for carrying out ongoing infrastructure changes. They can make high-level infrastructure requests via Jira, or they can make pull requests on the infrastructure as code repository. The Terraform for microservices is also modularized. So adding new microservices is largely a matter of parameterizing existing modules. So when a microservice has unique needs, it just requires us, that's the time it requires us to write a new Terraform module. And so at this phase, we started applying some of the lessons we learned from our pilot efforts. After the success of these initial efforts, we had a clearer sense of what kind of problems could be better solved by microservices. So now we are very close to completing work on a service that completely changes how we manage the core of our user-generated content. Obviously, there's a strong business motivation for developing this microservice. And needless to say, scalability is a critical requirement for this microservice, not just a nice to have. In addition to this key microservice, we've also already built a handful of microservices that are powered by our machine learning efforts and the efforts of our data sciences team. So this has been our journey in introducing microservices at Quizlet thus far. With that, let me hand it off to Scott.
Thanks, Amol. Now I'll talk about how we have invested on improving the monolith alongside the microservices journey. Let's start by recalling our monolith tech stack. Our programming language is Hack, running on the hip-hop virtual machine. This HHVM execution environment, along with our MySQL databases, Memcache instances, and ElasticSearch cluster, all ran on virtual machines in Google Compute Engine. Infrastructure observability was provided by a self-hosted Grafana instance and infrastructure management configured with Puppet. To handle asynchronous tasks, a homegrown internal batch job system we call Distributed Job Processor provides a pipeline for publishing tasks to Google Cloud PubSub that are executed by a worker deployment of our monolith. At Quizlet, the developing engineer is the change owner. Engineers are empowered to merge their changes and deploy the build to production. However, as we started to scale, we noticed growing instability in the minutes immediately after deploy. Web engineers loosened their trust in deploying and spent nervous minutes watching the deploy metric dashboards. We wanted to regain the trust and sense of empowerment in deploying new code to production. Also, we wanted the compute infrastructure to be more robust in the face of failures. Virtual machine crashes should not need immediate manual attention to resolve the problem. The system should be self-healing. Internal tooling was showing age. We were managing infrastructure using Puppet, a good start from an infrastructure as code perspective, but this Puppet configuration was quite old, predating a good number of our engineers. We wanted to explore the use of a more modern alternative to infrastructure management, something more ergonomic. Likewise, we wanted to have a more managed experience for our database and observability machines, something that didn't require as much babysitting. We split these efforts up into multiple projects that took about 18 months. By migrating deploying code on VMs to deploying containers on Kubernetes, we hope to reduce some post-deploy instability while increasing compute resilience. Moving Kubernetes meant we needed to revisit our mode of deployment from custom scripts managed by Jenkins jobs to continuous deployment system designed for Kubernetes. By migrating data stores on VMs to managed offerings, we offloaded the hard parts of maintaining reliable database infrastructure to vendors. We also took this opportunity to perform significant upgrades to our metrics and monitoring system. After evaluating a couple of options, we settled on using Datadog as a complete observability solution, both for metrics and distributed logging. Let's dig in a bit more. The largest investment we've made in our monolith was moving to Kubernetes from virtual machines. Not only did this transition align our monolith infrastructure with the microservices strategy, but it enabled us to tune existing deployment types for our monolith based on load test benchmarks, a testing strategy much more difficult when dealing with slow instantiation of virtual machines. So what do I mean by deployment type? We define certain flavors or deployment types of the monolith based on a request type. For example, while most requests are handled by the generic web deployment type, search routes are handled by the web search deployment type. This allows us to configure things like the virtual CPU and memory of a web search deployment container to better handle the high networking I/O weight of search requests. And remember, our asynchronous tasks are published to a pub subtopic and executed by the web worker type. Worker processes can run longer than a normal user request and are not expected to be executed instantaneously. Similarly, scheduled cron jobs execute in an isolated single-purpose container instance of the monolith. Cron jobs can also run longer than a typical request and can require large amounts of memory or CPU depending on the job. Since crons are not continuously running like worker jobs, the cron container is destroyed after its work is finished. So even though our monolith is much larger with a wider diversity of purpose than a typical service would be, moving to Kubernetes has allowed us to treat compute handled by the monolith with individual and tuned purposes in mind. Argo CD is a system with native support for managing Kubernetes deployments. Not only did Argo CD satisfy our Kubernetes deploy needs, but it offers additional support for deploy strategies like canary deployments. Similarly, we use the sister product called Argo Workflows to manage our revamped scheduled cron job execution system. When on VMs, crons would share a single virtual machine, and it was common enough for a bully cron to hog resources from other jobs. Argo Workflows provided a simple way to schedule and isolate cron tasks written in the monolith, disposing of the containers when complete. Persistent services, or data stores, can require a significant amount of domain-specific knowledge to manage well. Quizlet decided to take a buy, not build approach to platforms when possible. And one of these earliest transitions we made was taking our MySQL instances from VMs to the Google Cloud Platform's Cloud SQL offering, a fully managed database service. With Cloud SQL, we don't need to worry about establishing a custom process for failovers, backups, disk or compute scaling. And in the event some failure does happen, we have Google Cloud support available to us to better understand any underlying issues on our end. As mentioned earlier, we have a caching layer provided by Memcache to assist in handling MySQL queries. We further reduced the operational burden of managing infrastructure by migrating our Memcache instances to Cloud Memory Store. Similar to Cloud SQL, Memory Store is a fully managed offering. The theme here, less for us to maintain, more for Google Cloud Platform to provide. One could say we have an organizational bias towards cloud computing. Our site search functionality is powered by an ElasticSearch cluster. Another investment we made was upgrading our legacy version of ElasticSearch to a more modern version. And while GCP doesn't offer a managed Elasticsearch product, they do have a GCP marketplace integration with Elastic. And in the spirit of buy, not build, we decided to leverage a hosted service instead of implementing our own infrastructure provisioning. Again, the biggest advantage here was outsourcing operational knowledge to Elasticsearch vendor that specializes in it. Internally, we didn't need to learn all of the quirks of tuning an Elasticsearch cluster just for our use case. We could leverage out-of-the-box hosting and provisioning options available through this GCP integration. Observability is a system that works best with a single canonical repository of information. Otherwise, it's hard to correlate metrics across different observability systems, be it distributed logging, tracing, metrics monitoring. Because the microservices development was led by teams that are focused on solving a business problem, they weren't in a position to solve problems that required central solutions. As a result, microservices relied almost entirely on Google Cloud's built-in observability solution. However, once we had upgraded the monolith to use Datadog and paved the road for managing that part of our code as infrastructure as code, microservices started adopting this software as a solution too. So now that we've covered some focus areas for upgrading the monolith, let's take a look at how our monolith and microservices coexist today. A majority of our changes, improvements, and features are developed in the monolith. Microservices are coming. We have successful microservices in production, more under development, and more yet in the design and planning stage. So with multiple avenues of development, we needed to provide some guidance on how to go about choosing the right architecture for a project. We might choose to develop a microservice based on the ergonomics of a non-hackling programming stack. For example, our data science team is most proficient in Python, and the majority of libraries and tooling are also in Python. Therefore, it's a clear choice to favor a Python service over the hackling monolith for data science work. Another consideration would be the complexity of implementation design. Some high scalability use cases may necessitate a complex implementation, like denormalizing data persistence for faster access. Managing this complexity is easier in a new microservice, since the monolith is really geared towards use cases that fit existing access patterns. So if a data structure doesn't fit well into the existing monolith and MySQL patterns, the microservice is probably the way to go. If an implementation requires access to data managed by the monolith code, a microservice implementation would be cumbersome due to this dependency on monolith APIs. This asserts an encapsulation principle for microservice implementations. Microservices must maintain control over the data they manage. If microservices directly access data outside their scope, the microservices lose encapsulation benefits and is coupled to the monolith. We consider this concept of a distributed monolith an anti-pattern. If a feature under development is only a minor change to existing functionality, it's unlikely the cost of service ownership and microservice development outweighs the benefits of an encapsulated microservice. So here we'd stick with monolith development. All right, so there's clear differences in our monolith and microservice journeys. With microservices, it was quick to realize value. Microservices gave us a safe space to learn about the new world of containers and Kubernetes. And now we have a fast path to build and deploy data science services with production examples of extracting problem areas from the monolith and moving them into services. The monolith containerization took a while to bear fruit, but that fruit is very tasty and full of so much knowledge. We unlocked a deep understanding of Quizlet's existing infrastructure and continue to develop a majority of our features using this upgraded monolith. So, if you haven't been listening, now's the time to put your phone down and tune in. The takeaway here is that Quizlet is proud of and happy with the architectural improvements on both microservice and monolith fronts. Not only do these improvements lean on organization-led collaboration, helping us learn and teach ourselves something new, but both microservice and monolith remain strong vehicles to deliver on our mission. As our transformation marches forward, our monolith and microservices are better together. Okay, so we log a win in the book, pat ourselves on the back, but we know engineering work is never complete. The world changes. This is just round N of many. And Amol is gonna break down what's up next.
Thanks, Scott. In this concluding part, I will share some of the ideas we are planning to work on to continue to evolve our architecture. So if you recollect, this is our current hub and spoke architecture, and we constrained ourselves to this for simplicity. But with about a dozen microservices in production now, we're finding that this architecture is a bit limiting. For instance, if we must funnel all traffic through the monolith, then scaling the microservice horizontally also involves scaling the monolith, even if to a much smaller degree than if it was implemented all as a part of the monolith. And so it is clear to us that we need a first-class way to route traffic to the microservices by bypassing the monolith. Essentially, we need an API gateway to route traffic to services that need to be accessed directly from the clients. Now, some services like spam classifier, as seen in this diagram, may need to only be accessible in the backend via the monolith, and that's fine too. So to make this API gateway work though, we need to extract the auth logic so that auth can be performed at the gateway. And then microservice can continue to assume that the gateway relays the appropriate user identity. Another opportunity we see here is to double down on our containerization strategy by adopting a service mesh like Istio. Strictly speaking, service meshes and containers are orthogonal to each other, yes, but containerization gives a practical advantage in adopting a service mesh. And now, given that our monolith and microservices both run on Kubernetes, it makes it a lot easier for the service mesh to span all of our compute infrastructure. So what exactly do we intend to achieve with the service mesh in place? Service mesh would allow us to enforce network policies that span all of our compute infrastructure. It would enable us to do smart traffic management. Say we wanted to tee a part of our traffic to an experimental system. This could easily be implemented with a service mesh in place. Service mesh could also be one way for us to introduce distributed tracing across all layers. And then in order to provide a unified view into various aspects of microservice management, we're considering building a services dashboard. And finally, we will continue to invest in scalability improvements in the monolith. We are actively looking into third-party solutions that can enable horizontal scalability for the Cloud SQL databases used by our monolith. Finally, here's a parting thought. What we shared here may not necessarily provide the perfect blueprint for how you should go about solving your architectural problems. Hopefully, there are elements of our problems that are similar to yours, in which case you may find parts of our approach relevant. But really the meta message, if you will, is this: analyze your situation from first principles and gain a deep understanding of your problems. Be bold and devise architectural solutions that address your problems rather than mapping your problem to someone else's solution. And when you learn something in the process, come and share your story with us. We'd love to be in your place. So that's it for the presentation, folks. Thank you for attending this talk at the 8th Annual Denver Startup Week. We can take questions at this time.
So Connor, does the audience have a way to chat questions to us? Is that the preferred mechanism?
Hi guys, I think Connor dropped off perhaps, but feel free to put messages in the chat and we'll relay them along. Give it just one more minute here.
Okay, so I see a question here in Q&A. Are there increased challenges in debugging now that you've introduced this level of microservices? So, I mean, on the face of it, yes, because now you have more distributed components. But like Scott mentioned, one of the things we did in our monolith upgrade was introduce Datadog for distributed metrics gathering and distributed logging. And so that's our solution. Now we can view all the logs, we can query all the logs in a unified interface. And I think these kind of investments are really key if you want to have a productive microservices architecture. So hopefully that answers that question. Okay, there's another, what is an effective way to get buy-in for investments in decomposing the monolith with executive leadership? I think this is a great question because ultimately you want to do something that addresses or provides business value. And the way I prefer to do it, or the way we prefer to do it at Quizlet, is we always ask ourselves, what is the business problem we are solving? And yes, so if you recollect in our journey, the first part, we actually didn't solve any business problem. But that's because we knew that we will have use cases coming up or that we were already facing. But we didn't want to jump straight into the business use cases before first upskilling ourselves. And so we picked a small problem, which really took us a matter of a few weeks to just containerize it and put it in Kubernetes and get those quick learnings. But then we proceed. This is why like our approach was like, take one business problem, solve it, learn from it. And yeah, and then as you learn from it and as you solve problems, you not only can make this case more effectively with leadership, but you also get confidence, right? Like you've solved a business problem and now you can very confidently say, what are the other things you can do?
And
so
I'd like to add to that.
Yeah.
I'd like to add that executive leadership usually think more in terms of money than developer ergonomics. So I would always recommend taking the approach of, this is what a cost of ownership is today. And you're including all of the time you're spent figuring out what's going wrong with the system. Like, what is it costing us money from a development point of view? is it costing us money from a user point of view where we're actually losing users? But if you can compare a proposal where this is what it's going to cost to start transitioning, and then what the cost of ownership will be when that's complete, that's a more numerical approach rather than it'll be better for the developers.
That's a great point. Yeah. Just to round that out, we also did a analysis of cost of operating the new service compared to how we were operating in the monolith. And just on the huge part of the cost was obviously the databases. And without revealing too much, all I'll say is, as things turned out, we ended up spending nearly the same amount, like maybe 1 or 2% from what we were spending on the old databases, but this came at a much reduced ongoing investment in maintaining the databases. Okay, there's a third question. What about the developer experience? Does additional complexity slow developers? Is there a tax on development? Yeah, once again, the question is spot on, because in our initial efforts, there was a huge tax on developer experience because we did not have distributed metrics and logging in place. So we were relying on Google Stack Driver, whereas the Monolith was logging its Monolith logs were going elsewhere. So we did not have a unified visibility. Also, like I said, the onion diagram, like you have developers wanting to focus on app code, but then there's Docker, there's Kubernetes, there's Terraform. So all these layers of technologies, they are a significant upfront cost. And that's something you need to be aware of. Like you need to buy into the strategy and invest in upskilling engineers at the same time. And yeah, I guess there's another side to it, which is microservices, like the promise is smaller units and hence loosely coupled, and you can test them easier, deploy them easier. But all of that is true if you, again, make investments in continuous deployment, make investments in, again, automated testing, all of that.
And I see a question in the chat, Amol. How do you handle local development?
Great question. Thank you. These are really great questions. This is a problem we are actively working on. Because today our development environments are essentially what we call as full stacks. So they are like each developer has their own VM in the cloud. And this VM has the entire monolith, which made sense, obviously. But now with microservices, we also need to think about how can we enable microservice development alongside this full stack. So we have a couple of strategies that we are experimenting with, and Q4 for us is going to be nailing that piece of the puzzle. But currently the way we do it is we have a shared development environment where all changes to the microservice get, once you're merged to master, go through the CD and get automatically deployed to that shared development environment. And that's worked reasonably well so far, but yes, that's not going to be our steady state model. Cool. All right, we'll give maybe 30 seconds, but we're also nearly at time. Yeah, so just in case we run out of time, I just wanted to thank once again everyone for being here. These are very challenging circumstances, and we really appreciate people taking time out from their busy schedules to be here.
Cool. All right, well, yeah, I echo that. Thank you so much, everyone, for joining.
You guys did a great job. Thanks so much.
All right, take care.
Bye-bye.